So this section is about limits and continuity. Let's start with continuity before we move on to limits. Continuity in a function is exactly what it sounds like. If a function is continuous, then it has continuity. But not so easy to find always when a function is continuous. So we're going to look at some tools with which we can establish the continuity of a function in various ways. So suppose you have a graph, a picture of a graph, and a function looks something like, say, that. All right, so we know it's a function. It clearly passes the vertical line test. Let's say it goes off to infinity all the way through. And the question for continuity, a visual inspection for continuity, is to look at the graph and see, if I was a tiny bug, could I make a bug walk without risking my life? How likely am I to get home to see my family? So you can see that if this bug walks off to infinity, it's going to have no trouble walking along the path. If it walks in the other direction toward positive infinity, excuse me, this is negative infinity. If it begins to walk toward positive infinity, it looks like there's no place where the bug is going to have to fear for its life or use any sort of extraordinary measures. On the other hand, if that bug were to take this path home, let's make it almost the same just to create some clarity. And right here, there's a giant gaping hole, right? Then that same bug walking along this path would have no trouble getting off to negative infinity, but would have trouble here. Doesn't look like it would have a lot of trouble. It might be able to just jump over the top of it, but and move on about going home, but it could be a problem. It's an area where the path is discontinuous. All right, so this is a particular kind of discontinuity. We'll get to some more clarity about this later. This is actually called removable. And it sort of looks removable. It looks a bit like a pothole in the road. You come along, you fix the pothole, you go home, everything's fine. And that's a removable discontinuity because it's just one tiny little point. Of course, I've drawn a big circle, but that's because using the tools that we have, this is really meant to say at one infinitesimally small point, the graph just stops and then restarts. So let's look at another example of discontinuity. So suppose the graph does this and then comes to an asymptote. We love asymptotes, right? And then continues on. Well, let's try to map it as closely as I can to the other form or to the other side. So there. So this looks almost the same, except this is an asymptote right here. All right, so if this bug, again, starts home from work, apparently this is where he works, and he walks and walks and walks, at some point he's just going to hit an asymptote. He's going to continue on toward infinity. He's never going to get home. He's just going to be lost forever. So this graph clearly does not have continuity at this point, say x. Right, so clearly at this value there's no continuity here. If this bug's home is over here, its family is never going to see it again. So this is infinite, as you might guess, infinite discontinuity. Right, so at this point, infinite. All right, and one more example. Suppose the bug is headed home like this, and he gets right here and discovers that somebody's come along in the middle of the night and moved that road. Right? Somebody came through and said, oh Lord, we need a detour because we're going to do some road construction and we need to move that road. So here we have a situation where the very same bug takes off. And in order to continue home, it's going to have to, check it out, jump to get down there. So this is called a jump discontinuity. All right. So as we begin to work our way toward calculus, we care about continuity. What we really want is to always have a function that is smooth and continuous everywhere along its route. Discontinuities are disconcerting for us, but it turns out a removable discontinuity is pretty easy to deal with. We don't really care. A removable discontinuity is almost exactly the same as a continuity. We have a lot of tools to deal with that. Infinite and jump discontinuities, excuse me, on the other hand, are disconcerting, and we have to bring out some pretty powerful tools to work with those, if we can work with them at all. So as I said before, we're not so concerned about a removable discontinuity. We can work with that. And the reason we can work with that is we have a tool called the limit. The limit. And it has a notation. We write lim, L-I-M, as x approaches some value. And I'm going to say x approaches a. Okay, so as x approaches a, what happens to f of x? So this is the notation for the limit as we begin to evaluate them. So what does that mean, a limit? Well, let's look at the removable discontinuity. Okay, so we know that there's a hole right here. We know that there's a spot where the graph ceases to exist, and then on the other side of that hole it picks right back up again. All right, so what we want to say is, or what we're looking at, is as values of the function, as input values approach some point on the x-axis, from the left and from the right, we want to know what happens at that very point. Does that make sense? So let's come down here and let's look at the removable discontinuity a little bit. I'm going to say the limit as x values approach a. So this is going to be a. So all my x values approach a, where we know we have a problem. So if I choose x values approaching a from the left-hand side, what's happening to the y values? Well, the y values, as I approach, the y values go up, and then they come back down, and then they go back up, and they approach that spot. This is what looks to be happening to y as I move, as the bug walks closer and closer to that place on x. Right? So it's getting closer to whatever that point is, then it drops a little bit lower, but then it goes right back up and it starts heading right toward that point. Well, what happens from the other side? The other side is bug wife or bug spouse heads to meet bug. So bug forgot their lunch and heads back home to get it. Bug spouse realizes bug forgot lunch and starts heading toward bug to bring lunch to work. So as bug spouse approaches from the right, bug spouse is going to get closer and closer to the y value, kind of right at the same level, going to go a little bit higher on the y, but going to come right back down and head toward the exact same y value. In fact, as bug spouse gets closer to a on the x-axis, bug gets closer to a, and they can hand off that lunch, give each other a little kiss, and move on. And this is useful because if we want to determine the continuity of a function, we can do that taking into account maybe a point doesn't exist, or the line or the curve doesn't actually connect at some point, but we can decide whether or not it does or does not connect using the limit. And here's how. So we can use the limit to determine continuity at a given point. All right, so here's how we do it. It takes 3 steps. First, if I want to know, and let's go back up here to our continuous graph. My question is this graph continuous at x equals a. Okay, so I'm not asking about what's happening over here or what's happening over here. I'm only concerned about this little area, and I want to know, is the graph continuous at x equals a? So I have to ask myself, this is what it takes for it to be continuous. It has to be continuous on the left-hand side, and it has to be getting closer and closer to a as I move on the left-hand side. It also has to be getting closer and closer to a as I approach from the right-hand side, and it actually has to exist at a. So there's some logic there, right? If the graph is moving toward a on the left, moving toward a on the right, and actually exists at a, then it's continuous at a. So the notation for that is the limit as x approaches a from the left, that's what that little minus sign means, I'm coming from the left, of f of x, if it's continuous from the left and it's continuous as x approaches a from the right, and the minus and plus are intuitive. If it's from the left, meaning if you move from the negative side, and then you move from the positive side, that would be from the right. And if it exists at the f of a. Okay, so that means if it actually exists at a, then it's actually the point. The point exists. If it approaches from the left and it approaches from the right and everything is pointing toward f of a, done. Then we have continuity. So easy in theory, so much harder to do in the real world. So let's do an example. All right, so we're asked to determine whether this function is continuous at x equals 1/2. And right now, I mean, we could sketch this graph using our Algebra 1 tools, right? This is the parent form, y equals 1 over x. X has a 2 in front of it, which means we have a squeeze or a stretch of 1/2, and then plus 1 is to the x, not to the y, so we know that the whole thing is going to move backward or forward. In this case, plus 1, the whole thing is going to move in the negative direction. And so I know that I'm actually going to end up with a graph that looks like this, right? But we aren't going to have to do that. Sometimes you need to be able to kind of get a rough sketch or a rough idea in your own head, but we're going to use a calculator for it. So I'm going to pull up my calculator. If you have your own calculator, I've said this before, let me say it again. If you buy a graphing calculator, please make sure it has CAS function. You're going to find that it has tools that you need, solving tools. I'm mostly only going to let you use your calculators for checking your work, and you get more meaningful checking of your work by using a CAS calculator. So I don't recommend that you buy one. We have some in class that you can use when you're there. And if I were to give you a test, I would give you this picture. I'd probably use my calculator. I'd take this picture and give it to you, so you'd be able to see what I would be looking at on a calculator, or I would let you use the calculators in the room. Okay, so anyway, you can see that I've already entered the function into my calculator. I just used the graph diamond y equals. So I get the green diamond gives me all of these green functions on these keys. And so I've entered the function, and now I'm going to graph it on my calculator so I can see what it looks like. And I'm hoping it looks exactly like I've shown you, because I've shown you that. Exactly. And here's the asymptote, which has moved back to, I'm not really sure where that is, but if I trace I forget, I can't touch the screen. Let's see, trace is F3. So if I trace my function to get close to this asymptote, I can kind of see where it's going to live. And I see that the x value, it's at minus 1/2. So this asymptote is at minus 1/2. And check it out. That's exactly what I expected, right? Because, well, that's exactly what I expected. So now that I've graphed my graph in, now look, I've got an asymptote, so clearly the function isn't continuous everywhere because the bug wife would be going off to positive infinity while bug is going off to negative infinity, and that's not a good thing at that point. But they're not asking us to evaluate it at negative 1/2. They're asking us to evaluate continuity at positive 1/2. And at first glance, it totally appears to be continuous. In fact, as I continue zooming back in the other direction, I can see by looking at my x values that as I get closer and closer and closer, let me get up there, to 1/2, that I'm getting closer and closer to 1/2. In fact, my numbers, notice, are bigger, 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 getting smaller, smaller, smaller. And then once I cross over the boundary to 1/2, then my numbers start getting smaller, smaller. So it looks like I'm actually continuous at that point. But because we're talking about points being infinitely small, it's possible that there's a hole there, that there is a point discontinuity or removable discontinuity that I can't see on the calculator. So I want to use a table to evaluate these points. So if I set up a table, x and y values, and I'm going to put 1/2 right here in the middle, because that's what I want to see, is what happens at that point. And then I want to choose values bigger and bigger than 1/2 and smaller than 1/2. So I'm going to use 0.5 as my value for 1/2. So on the right hand side, my numbers should be getting bigger and bigger. So at 0.5, I'm going to choose hundredths, 0.51, 0.52, 0.53, and that should be enough. And on the other side, I want to get closer and closer. So I'm going to say, what would that be, 0.49, 0.48, and 0.47. So now I've set it up. First, remember, we have 3 conditions to prove continuity. One of them is, what is the function at f of 1/2? Does it exist there? So let's go ahead and look at that. So the f of 1/2 equals 1/2 times 1/2 plus 1. Well, that's 2 times 1/2 is 1, plus 1 is 2. So at 1/2, at f equals, at x is 1/2, f of x, or y, equals 1/2. So 0.5 and 0.5. And that's exactly what we kind of saw happening when we were tracing through the graph. But we want to know what happens as the limit of x values approaching 1/2 from the right of the function. What's happening to the limit? What is the limit getting closer and closer to? And I can tell by using the graph, I could tell that it was getting closer and closer and closer to 1/2. But we want to use the table, and luckily these graphs give us really great table features. So notice here is 0.5, and it tells me my table, when x values are 0.5, y values are 0.5. That's exactly what I got. But as x values approach from the right, so 0.51, what's the value what is the graph value? 0.495. At 0.52, it's 0.4902. And one more. At 0.53, graph value is 0.485. On the other side, and we can tell that as values are getting bigger and bigger and bigger, as x values are getting smaller and smaller and smaller, approaching 1/2 from the right, that y values are actually also approaching 1/2. So we can say that the limit from the right exists and equals 1/2. And then let's look at the limit as x approaches 1/2 of 1 over 2x plus 1. What's happening on this side? So let's look at the other side. 0.49 has a value of 0.505. 0.48 has a value of 0.510. 0.47 has a value of 0.515. And so you can tell that as you approach from the left-hand side, that the values of the function are getting closer and closer to 0.5. And so we can say that the limit from the left-hand side is 1/2 as well. Since the three-pronged test has been met, the function exists and equals 1/2 from the left, it exists and equals 1/2 from the right, and it exists and equals 1/2 at the function point, we know that this function is continuous at x equals 1/2. By the way, I wanted to show you that you can also do this with Desmos. So let me close my calculator. I've set up the function on Desmos, and if you go, I'm off the screen, but you can see where my finger is pointing here, or my arrow. If you go straight up from here to the little flower, the cog, you can choose to turn this and convert this into a table, and it'll show you x values and y values. So these have been plotted in. Now the one that we care about is actually right here at x equals 1/2. So you can choose to just label the points what you want. So 0.5, and I can put this one in at 0.49 and this one at 0.48, and then let's do 0.51 and 0.52. So I've actually labeled in these values, and you'll notice that the values that Desmos gave me were exactly the same values that my calculator gave me. But also notice here, it looks like there's only 1 point, but there's not, because if you zoom in, you can see that these are values approaching x equals 1/2. Right? So this is this whole string of points as you approach from the right, as you approach from the left, and then what is at exactly x equals 1/2. So you're not limited to using an in-class calculator, but you won't have access to Desmos on a test or a quiz, most likely. But you're certainly welcome to use it.